Starting in with some problems here from your assignment. And problem number 17 looks at sig figs. And of course, we're always interested in sig figs. Remember, don't lose sight of the idea that the reason we're worried about sig figs, excuse me, is so you will think about sig figs in terms of how precise your instrument was that made these measurements, so that we can't pick up additional sig figs from our original measurements when we're doing calculations. We can't increase the sig figs, but also that you'll find ways of making measurements with instruments that give you the maximum potential for sig figs. So if these were hydrogen ion concentrations, I think that's what they ask you about initially. How many sig figs would there be? Well, there'd be 4, 3, and 2. But if those are pHs, if those are actually pHs, they're logarithms. Remember, pH is the negative log of the hydrogen ion concentration. So if you want to go backwards from this pH and find the hydrogen ion concentration, you take 10 and raise it to the negative pH. Well, since these are logarithms, these decimals these numbers in front of the decimal point just give you they're placeholders. That tells you how far you're moving the decimal point. They are not significant digits. The only sig figs are the numbers after the decimal point. So all of these, if those are actually pHs, all of those only have 2 sig figs. Number 19, you can work through this and find some examples in the book, but what you really, this is the thing that you're supposed to learn from each one of these problems, and that is that here we're looking at a strong electrolyte, meaning it's dissolved in water, and this electrolyte is very acidic. Well, that means we're talking about a strong acid like hydrochloric acid. Now in B, you're looking also at something that's totally dissolved in water, but it's only slightly acidic. And to be totally dissolved in water, it can't just be a weak acid and be slightly acidic. It has to be the conjugate acid of a weak base. And so maybe you have ammonia, NH3, and that in combination with H2O produces NH4 plus and hydroxide ions. So this is the conjugate acid of a weak base. So if you have something like maybe NH4Cl, well, you dissolve that in water, it's going to be a strong electrolyte, and so it's going to dissociate into the separate ions, and here you have a slightly acidic solution because of the presence of the NH4, the ammonium ion. So you might think of several examples of that. A strong electrolyte solution that's very, very basic, and once again it's very soluble in water, so this would be a strong base like maybe potassium hydroxide. A strong electrolyte that's slightly basic. Once again, we have strong electrolyte, meaning it totally dissociates in water. It's soluble in water, but it's only slightly basic. So we're looking for the conjugate base of a weak acid. So you find a weak acid like maybe HF. Well, that's a weak acid. The conjugate base, because that's gonna, if that combined with water, you'd have a fluoride ion and H3O plus. So here you have the acid and its conjugate base. Now the conjugate base is going to only be slightly it's going to be slightly basic. So if you have something like, sorry, here I get this finally out. If you have sodium fluoride, it's going to be a strong electrolyte, but the fluoride ion that's present is going to make this slightly basic. And we'll look more at that as the chapter progresses here and as we move on into other chapters. A strong electrolyte, that, let me get this so I can read that, a strong electrolyte solution that is neutral. Well, this is going to be the salt of a strong acid and a strong base. In other words, something like sodium that comes from a strong acid, and chloride that comes from a strong base. That's going to be a strong electrolyte solution that has no acidic or basic properties, so it's going to be a pH of 7. Whew, that was a long one. Okay, we're looking here at number 24 on your assignment, and I'm trying to remember what the question is. I think it's pick which of these solutions, for each of these solutions, decide, is it A, B, C, or D? I think that's the question. And so look at that and give it some consideration. Well, this is a weak acid. And so because it's a weak acid, the hydrogen ion concentration is not going to be this big. In other words, when this dissociates, it is not going completely to the right to make hydrogen ions and HCO3 minus 1 ions. It's not going to make just that. So the hydrogen ion concentration is actually going to be less than the 0.1 molar. Here, this is a strong base, so it's going to dissociate into all the 0.1 moles of sulfuric acid is going to dissociate into 0.1 moles of each of these ions. And so the pH, or the hydrogen ion concentration, is going to be at least 0.1, but this can dissociate a little bit further in equilibrium system, and so it's going to contribute a little bit more, but not nearly enough to make it 0.2 molar. So this is going to be C. 25. Of the hydrogen halides, only HF is a weak acid. Why? Well, to get the answer to this, look back at some of the previous videos where we talk about the strength of the bond between the halide and the hydrogen. That's what I'd suggest you look at. Maybe even think about electronegativity differences, things like that. Number 28. I believe in number 28 you're supposed to write the dissociation reaction like I've done here in black, and then write the acid dissociation expression for each of those. So study that example and you can finish number 28. For 29, you should be able to go through these and identify the acid, the base, the conjugate acid, and the conjugate base. So for example, here I am looking and I see 3 hydrogens, but over here I only see 2. It means that this species has given up a proton, and this is what remains. So this then would be the acid because it's a proton donor, and this would be the conjugate base of that particular acid. So study that example, look at the examples in your book, and answer question 30. Oh, by the way, Water sometimes can be an acid or a base. In this particular case, it is acting as a base because it's a proton acceptor, and this would be the conjugate acid of that base. It almost seems earlier like I had that as a conjugate base somewhere, and I don't know how I would have said that. Well, I'll quit pondering that now, but hopefully I didn't make that error, because H3O plus is always a conjugate acid.